So it more commonly in the past, but still done today. When you have an unknown substance, you would run either gravimetric analysis or some other test, and what it would return to you was just the percentage composition of the elements. So you would get something back that says the compound that you submitted is, and I'm trying to find a good example. These are ones I cannot just do off the top of my head because the numbers have to work. So we would get information back that says that a particular compound is darn it. You would get back information on analysis that gave you something like this. Well, the compound you submitted is 32.38% sodium, 22.65% sulfur, 44.99% oxygen. That doesn't give you a formula. So what you can find from this is what's called empirical formula. And the empirical formula is the smallest whole number ratio of the atoms in a compound. Now, ionic formulas are already empirical. It's already the smallest whole number ratio, because that's all an ionic formula is the smallest whole number ratio. But in molecular compounds, you get this. You can have a substance that is CH4. You can have a substance that's C2H8. And you can have a substance that's C3H12. Those are the molecular formulas. An actual molecule of this substance has 1 carbon and 4 hydrogen atoms. An actual molecule of this has 2 carbons and 8 hydrogens. An actual molecule of this has 3 carbons and 12 hydrogens. So this is the molecular formula. And this distinction is really important. Even though we're not going to go heavy on the math with this, you have to understand the distinction between molecular and empirical. The empirical formula is just the smallest whole number ratio of the parts. So the empirical formula for CH4 is CH4. It's already the simplest whole number ratio. The empirical formula for C2H8 is CH4. And the empirical formula for CH3 is, or C3H12 is CH4. They all have the same empirical formula. They have different molecular formulas, but the same empirical formula. So the kind of information that we would get back on, like gravimetric analysis. They precipitate it out, they separate out the component pieces, and they mass them, is really percent comp. So if we go back to this, we get this information back. From that, we can actually find the empirical formula. And to do that, we have to compare, because what is this? It's a ratio of the number of moles of carbon and hydrogen. For every 1 mole of carbon, there are 4 moles of hydrogen in each of these. It's a mole ratio. So with this, we can look at these percentages and figure out how many moles of each there are as ratios. To do that, we have to get a number of moles. And right now we're sitting here in percents. We don't have a way to get from percent to mole. We have to start out with grams if we're going to find the number of moles. So what we do is we imagine that we have a 100-gram sample of whatever this stuff is. Well, if we have a 100-gram sample of it, how many grams of that would be sodium? 32.38. It makes the math really easy. So we say, okay, in a 100-gram sample, we would have 32.38 grams sodium. How many moles is that? Well, we know that sodium has a molar mass of 22.99 grams sodium in 1 mole sodium. So we have 1.4084 moles of sodium. Okay. Well, we have to do this for each of the elements in here. Okay, so now I know how many moles of each of these things I would have in a 100-gram sample, but that still doesn't give me a ratio of one to the other. So, if I give you any things, you know that a ratio is a division problem in essence. So I'm going to look for the smallest number of moles of anything, and that is sulfur. So I'm going to then use that number of moles of sulfur as sort of my 1. And I'm going to divide each of these by 0.706, etc. Okay? Okay, so we'll focus on the first one first. I took the number of moles of sodium that I had, I divided it by the number of moles of sulfur that I had. I get 1.994199609. Pretty darn close to 2. So based on the numbers that I've got, it's looking like I have 2 moles of sodium for every 1 mole of sulfur that I've got. Now, sodium's easy because it's my 1. So for every 1 mole of sulfur that I have 1 mole of sulfur. Duh, that was easy. And then my last one is my oxygen. So I have, whoops, switched colors. So I have 2.8118, etc. moles of oxygen divided by my 0.70626 moles of sulfur. What do I get? I get 3.98137. Gee, awful close to 4. So I would say that the empirical formula for this stuff, and this is probably, looking at it, this is probably a ionic compound. We can use this for ionic compounds or molecular compounds. We're just finding empirical formula. If it's ionic, it's going to be the actual formula. So it looks like I have, and I'm going to write these in yet another color, 2 to 1 to 4. So if I wrote this with my subscripts in here, I would write sodium 2, sulfur is a 1, oxygen is a 4. Does that look like anything to you? Look like a familiar compound? What is it? Sodium sulfate. This is sodium sulfate. Now we can get some where it's not quite so obvious. We can get some where we have, you know, a subscript on the S because there's a different ratio. But you'll notice that if we blocked that off, it's very clearly sodium sulfite. We're going to do one, here's what I'm going to do in terms of assessing this. I am not going to make this a regular thing you're tested on. But I'm going to put a bonus question on the test that will be this. So you want to earn yourself some bonus points? Brush up. I'll make it worth your while. I'll do the things that normally I test as part of this unit. I'll leave on the test maybe, but I'll make those bonus. So I think that's a fair way to handle it. Okay, we have this stuff. We're told it's 26.56% potassium, 35.41% chromium, 38.03% oxygen. We got to make our imaginary 100-gram sample and set up our stoichiometry. That part's easy. Okay, we've got these all set up. We're ready to get the number of moles of each of these that we would have in a 100-gram sample. So we have the number of moles of each of these. Now what do we have to do? Take the smallest one and divide everything else by it. So potassium is our little one. Okay, fantastic. So we've got, for every 1 mole of potassium, we have 1 mole of potassium. For every 1 mole of potassium, for every 1 mole of chromium, we have 1.002 moles of potassium. And for every 1 mole of potassium, we have 3.499 moles of oxygen. So what are our subscripts? Remember, we're going to derive our subscripts from these numbers. So, does it look like this? Where these would be 1 and 1 and 3.5? Have you ever seen a subscript that was a decimal? How would you make those whole numbers? How could you do that and maintain your ratio? Well, 10, 10, 35, but that's not the simplest, that's not the smallest whole number ratio. We want the smallest whole number ratio. Something's not divisible. What if we doubled them all? And then we would have 2, 2, and 7. Those are the tricky ones. And you'll see those. You'll get something that's, actually 2 and 2 and 5. And so you get 1, 1, 2.5. And you're like, ugh. And people will want to round up to 3. And you can't do that. You've just blown your ratio. So you have to maintain the ratio. It's totally legal to multiply everything by 2 to get it to even. But you can't just round up that big a chunk. Okay, I'll give you the practice sheet, and you'll work on that. Like I said, I can give you one homework problem on these, and then Monday we'll cover the last mathematical concept. Tuesday we'll grade the homework. Wednesday's your test.